Alright, so my title is Gage fields. I'm going to explain in a moment what that is in an infinity one topos. I'm also going to at least indicate what that is, and most of all I'm convinced you that these two things need to be combined, that there's something to be done here. In order to do that, let me start with a vague but important motivation for one of these things. It need not be the only motivation that comes to mind, but it's really a very important one. It comes from physics. So, in something called quantum field theory, we won't hear much about this, but I want to mention this motivation. People like to consider the following setup. They consider some object called a target space. For my purpose, it will be called X. And I'll start my first example now by telling you item by item what you should have in mind with these things. This example is the simple example, which is well understood and classical. So the point of my talk will be that after I've stated the example, I will point out how we need to go beyond it and how it's not classical knowledge how to go beyond it. This will be the point of my talk. So the classical example of this target space is physical space-time. So that means, for all purposes here, it's some four-dimensional manifold that you may think of as being equivalent to the Riemannian metric, even though that will play no real role for me here. So something like so in this target space, we want to do physics. We want to understand how little particles propagate in X. For that, we introduce something called a parameter space, called sigma. What's called the world volume. What's it called that? Because here, in this simple example, we want to think of the sigma being the real line that we think of as the line along which the time, the internal time of some particle is being counted, such that a field configuration for the system is some map from parameter space to target space, which here is a trajectory. This is the world line of some particle. And we have some trajectory. A map from R1 to X, we think of as path of some particle propagate. Now the important point is that the talk will be about this particle won't just propagate there, it will experience certain forces. These forces are encoded in the non-trivial kind of concept that I'm going to talk about. There will be a differential co-cycle. I'll say what this is roughly in a moment. Differential co-cycle nabla on X. In this simple example, we think of this particle as being an electron that's maybe charged on an electromagnetic field. This co-cycle nabla is what's called a connection on a spinor bundle over X. On a vector bundle E over X, which is associated by some spin representation to the canonical spin bundle of X, where we now assume that, I'll come back to this point, I have to assume X has a spin structure. Say more about this in a moment. It just means for our purposes right now, for this example, there is some spin bundle to V spin D principal bundle P, where V spin principal bundle means it's some principal bundle lifting a then bundle corresponding to that spin structure. We haven't got these terms before, never mind, it just means some structure here living over X, and the point is we have this connection, and this connection encodes the forces on the particle. How does it do this? This connection is a rule gamma, smooth paths gamma in X, sends each of the points to a vector space, namely to the fiber of this vector bundle over that point, and assigns to that path a linear map between these vector spaces called the parallel transport of the connection nabla along that path, gamma, such that this assignment has all the nice properties that you would immediately guess it has. It turns out, by mechanisms which I won't get into here, but by well-known stuff known from the beginning of the last century, that such an assignment is, first of all, differential refinement, what people call differential refinement of this bundle here, and second, something in the physics picture that does describe the forces, in this case actually the forces of gravity on this part. So that's the classical input of what quantum field theory would be called a sigma model, quantum field theory, and this is just the classical data. Now we want to produce the quantum field theory from this. We know, or you may have heard or read in the news or something, or taught in class, that it's the first textbook example of standard quantum mechanics, that there's some procedure here called quantization, which produces something that looks very, very similar to what I've just drawn, but living not on exponent parameter space. Quantization produces a differential cocycle on sigma, namely a rule, usually called U or Z or something, I'll call it U here, that takes 2 points in sigma, which is the real line for us, so I'll call them T1 and T2, because we want to think of them as being eternal times. So then there are not too many options to have a path between them. I won't label this path, therefore, but assembly is just a path from T1 to T2. And we want to assign some vector space to these times, and these vector spaces are, I'll be a bit vague here, but they are vector spaces of sections of this vector bundle E here. Square integral, so there's some extra structure here which doesn't matter, so we assign this to each of these points, and then to this path here, we need to assign some linear map, and that linear map is famously known as the exponential 1 over IH bar, some physics notation where we take the square of our differential cocycle here. We use this connection on the bundle to produce a Laplace operator. Also not important for my talk what this is, but just so you know what I'm talking about. We place the role of the Hamiltonian of the system and multiply this by T2 minus T1. There's the parallel transport of this connection nabla square dt on the world line, and there's this process getting us from here to there. So this is very classical stuff, and lots of work these days on foundations of quantum field theory concern this quantization step, which I'm not going to talk about much, but let me just write it down. Differential cocycle nabla square c dt on the sigma. So you could ask, okay, so this is all well understood, so what's this all about? The thing is this, now we want to increase the dimension of sigma. And as you've seen here, I didn't quite explain why that comes in, but there was this funny condition that we need a spin structure here on X, and this spin structure kept entering this description, and that controlled the nature of this bundle here, and thereby also the nature of this connection. It turns out maybe I'll put this here. So as we increase the dimension of the sigma of lim equals n, these constraints, these extra conditions that we need on the topology in X, they increase. So it turns out as n increases, there are ever more stricter requirements on the topology of X for the quantization step to make sense, which I haven't explained to you what it is, but just take it for granted. for this to make sense, these conditions are called, a certain quantum anomaly has to be cancelled. So there's really, well, never mind. So there's some condition here, and it works like this. So we started on X. Say at the beginning might just have been an oriented manifold with a remaining matrix. So we know that the tangent bundle has some classifying map, the classifying space of the orthogonal group, OD. So turns out you can play this game with n equals 0. You can take the sigma to be a point, which is kind of an exotic case, but one can consider it. One finds for that to make sense, one needs that the target space that we're working on is oriented. Well, it's oriented, but one needs to pick an orientation which amounts to picking lift of the classifying map of the structure bundle, of the tangent bundle, to an SO differentiable bundle. The case we've just seen, this was n equals 0, the case we've just seen was where we see, oh, we need to lift further to the simply connected cover, the universal cover of SO, which is the spin group. Spin D sits over SOD as the universal cover, and we saw the entire input here was encoded or based on a string structure, which is precisely such a lift here. Now it turns out you can go higher. The next step is n equals 2, where the sigma is a two-dimensional gadget, which, if you think of the time coordinate as running as it did before, sort of in one direction, it describes some one-dimensional objects in x to the wolf in time. These are called strings. It turns out for this to make sense, you need a lift of the structure map to one even higher connected cover of the orthogonal group. Spin D has all homotopy groups in low degrees vanishing. The next one that's not vanishing is the one in degree 3. If you co-kill this, so if you take the universal 3 connected cover of the orthogonal group, you get to a topological group that has come to known as the string group. So write this as B string D. It sits over spin D, and in order for superstrings, for splitting strings, sense on some target, we need a lift of the structure map to this thing, string D. And now something interesting happens that will affect our story over there. You see, in our story here we started with some topological data. I said there needs to be this lift string structure, but then at this point I started doing differential geometry, and I said, oh, there's this smooth assignment here of certain data to pass, a smooth way. Of course this works because the topological group spin, as we all know, has canonically the structure of a Lie group. There's a smooth structure on there. This thing here, string D, does not have the structure, well, it certainly doesn't have the structure of a finite dimensional Lie group, because for all these, I3 does not vanish. So something with our story will go wrong when we get to this point here. And part of the point is to restore that problem. Before I get to this, I'll just indicate that this keeps on going here. It doesn't happen much now for a couple of n's here, because there are no further homotopy groups in the orthogonal group. The next one is pi 7. So as we come to n equals 6, we can look at the universal 7 connected cover of the orthogonal group. That group, again a topological group a priori, has become known as the 5-brane group. Because having a lift of the tangent bundle classifying map to all the way to B5-brane turns out to be the condition for the cancellation of the abstraction called the quantum anomaly that allows you to look at 6-dimensional spinning things propagating in X. So all this concerns the physics, if you wish, the formal physics of these extended objects. If you believe there's a reason to describe physics of such objects, otherwise it's just a mathematical exercise motivated from physics, of course. And our two examples here, which work for over 100 years in a nice way, breaks down the next non-trivial step. So we need something. So the big question is here. In order to make progress with the story is, where do the objects, what are these objects really? Where these objects is our sigma, our x, the space of maps between them, maybe also the nabla and so on. Right? And of course our string, etc. So where do I have to think of all this actually taking place? That's the first question. The answer to that question will be, these will be, so there's a natural way to make sense of this. All this needs to take place in a context where smooth objects of a more generalized sense than just bare manifolds exist. So the answer here will be, these are generalized smooth spaces. Namely, we'll make this precise by saying there are objects in an infinity, 1 topos. A higher categorical version of a topos. You may know that a topos has famously been suggested and tested to be a good suggestion to be a context for generalized spaces. We need generalized higher spaces here to make sense of this tower of higher groups here. So there will be something called an infinity topos, generalized smooth objects of, you should think of this, of Lie infinity groupoids. And it turns out that these objects here, they are no longer ordinary Lie groups, they will actually be higher Lie groups. Categories, the structure of the Lie group and the smooth structure. But these things are, in a natural way, Lie n groups for some n. This will be a Lie 2 group, this will be 6 group. There will be objects in this generalized smooth context, which I'm going to define in a moment. This will occupy most of what I can say in the time I have here, but I do want to indicate how to go further. The next thing is, I should have put this here. What precisely, so once we have these objects, what precisely is a differential cocycle? Hence physically a gauge field like the electromagnetic field. In our topos, so let's give this thing a name. This thing for me will always be called boldface H, because it will be a thickening of ordinary cohomology in a way that I'll mention in a moment. So this boldface H thing, this context for generalized smooth spaces, I want to know what is actually this assignment, of parallel transport data to smooth paths that we had here. And the answer to this will be there is in H an assignment, a functor, say on H, a functor, boldface pi, capital pi, is supposed to remind you of homotopy groups. It in a way encodes everything that's usually encoded in homotopy groups. It goes from H to H. It sends some generalized smooth space, a Lie infinity groupoid, to its homotopy smooth, homotopy empty groupoid, which is a big term for the simple idea that is still vaguely visible here on the board. It's the collection of all paths, paths between paths and paths between higher paths in this generalized smooth space X. And if we have this, then say that given a cocycle, as we had before, so we have our string thing now sitting in X, in H, so we will be able to say something like it's a smooth cocycle, that is in the smooth realization of string D, realizing a smooth string bundle. We also have X, as you can, I think, easily imagine, sitting inside the path infinity groupoid of itself as the space of constant paths. So we can ask if we can extend this diagram here, which will mean that we start assigning to each path some value here in the string in a way that's compatible with all these compositions. And this will be then say that this here is a flat differential string background gauge field with vanishing field strength. So it's a simple case of a generalization of this electromagnetic field example with some extra condition, flatness, which we can get rid of, but I won't talk about this. So this simple case is easy to explain. The no-flake case is not so easy to explain. And then the third point is describe the quantization. And I'm not going to talk about this now. I want instead, in the remaining time, give you a quick but precise impression of how points 1 and 2 work in detail now. So this was the motivation part, that was vague, and now I'm getting to definitions, some propositions hopefully. So it's an old idea, as I mentioned before, going also back to the Weir, who I assume you know, that, read point 1, that a good way to model generalized spaces, modeled on some test spaces, in terms of sheaves on the category of these test spaces. So old idea, for C, a category, well, for those who know it, this will of course in a moment be a category with the structure of the site, but for the moment just a category whose objects we think of tests as we think of as test spaces. So for instance, take C to be a category of ordinary manifolds. It's called diff when I'm writing it. Objects are smooth manifolds, morphisms are smooth maps. These are well-behaved smooth spaces that we have under control. I'll actually do something more simpler, more elegant. We take, let's say, inside there, just the Cartesian spaces. The full subcategory on manifolds of the form R to the n simply, with smooth maps though between them, not linear maps or something. So we just look at manifolds of the form R to the n. You should remember that a manifold itself is just something looped from R to the n. So since we're talking about just testing things, it's just as well testing it with, in a sense, with these Cartesian spaces and Gauss manifolds. So suppose we have these test spaces now and say, okay, whatever generalized smooth space I have, I just want to be able to test it with these by throwing in Cartesian spaces. So then, Rode, Weir, others taught us that what we're supposed to do is we take this category C and then set, sorry, is this going to make sense? Old idea. So you categories objects, we think of as test spaces, regard the sheaf topos. So it's a category of sheaves called the topos. So how does it work? It's called sheaves on C. Well, you know pre-sheaves on C. We've seen this morning already. This is just functors from the opposite of C to Z. We're looking for some subcategory in there. And we have those objects that know how our test spaces glue together, such as the inclusion as a left exact, left adjoint, some technical conditions. So we say this geometric embedding of toposes in the pre-sheaves, fixed by some topology on C that encodes the information how many Cartesian spaces may cover a single one. And then this, I'll call it curly tau, this here, regard the sheaf topos as the category of generalized spaces, modeled on C, modeled on the objects in C, modeled on C. Example? Well, it still says example. For our case, sheaves on Cartesian spaces contains Bayoneda and a bit of gluing technology, ordinary manifolds. They sit in there. But also more flexible things like what's called differential spaces sit in there. Differential spaces. You sit inside there as the concrete, what's called the concrete sheaves, so that those that do have an honest underlying set of points on which there is a smooth structure. And even more weirder things, right? Following the old Grothendieck dictum, we have this very nice category of sheaves here. There will be some objects in there that look maybe a bit too general than what you would have hoped for at the beginning, but they are in there. In particular, since as any topos this will be Cartesian closed, our home space, which really crucially enters the quantization process, even though I haven't told you, because that's the space of all paths in X, and some of these quantizations that will involve an integral over this path space, the path integral. In particular, the mapping spaces like sigma comma x exist as smooth spaces in there, as differential spaces in there. And thereby also we have a chance of realizing this path and this homotopy infinity group as a smooth structure, because it's k-dimensional cells are supposed to be smooth maps from k-dimensional standard paths, like the standard smooth k-simplex or something, into X. So that's a standard old story, but it's still not quite sufficient for what we need to do. This thing, the string group that we're after, is still not quite a group object even in there. And the higher ones, the 5-brain, 9-brain one, they will be even less objects in there. But already Grothendieck knew that something was amiss with this picture, and he started to pursue stacks. He said, oh no, this won't in general be sufficient here. We have just to have just spaces where I only know the set of possible probes by a given test space, because that's precisely what such a sheaf encodes. Now we have to go higher. We have to account for the fact that our general spaces here may have themselves internal notions of internal morphisms or homotopies. So what we need actually is the categorification of this picture. Where we don't just have smooth spaces, but smooth infinity group poles. Where smooth spaces go to smooth or Lie infinity group poles. This is known in the literature and several terms. Some call this higher geometry, some call this derived geometry. The idea is the same as before, only that we very systematically embed now everything into higher category theory. So we're after some big space, some big category, which will be an infinity category, infinity from one category of generalized spaces. Still my same C as before. Somehow I want to make sense of saying we have an infinity sheaf on that. I'll say in a moment what it is, and this will be my H. This generalized, this infinity topos of generalized smooth objects. So how would this work? Well, let's just copy the things we did over there. So we know whatever these things are, they should be probable by our test spaces. So it should be pre-sheaves on C that send each test object to the infinity group out of possible possibilities to map that test object into the infinity group out to be defined. And this will be just category of infinity functors from C op to the infinity category of infinity group words. Whatever that means. Yeah, what does it mean? So there's a nice intrinsic way to say what this means, but to give you a quick idea of actually, to give you an impression of we actually do something concrete, let me give you a convenient model for how to present these things. Just look at the ordinary category of ordinary functors. Maybe I should put this here. So we do ordinary functors. Let me call them simplicial pre-sheaves on C. This will be just the ordinary functor category from C op to the ordinary category of simplicial sets. These simplicial sets are in a moment going to give us a presentation of infinity group words. This category of functors, famously, after Joyal's letter to Grothendieck, then later developed by Jardine, and Dagger and others, carries the structure of what's called a model category. So there's some extra bells and whistles to this thing, which are geared such that there's a way to take a full subcategory here, which is what the circle is supposed to denote. Full subcategory on nice objects, on certain object called the fibrant cofibrant objects. And this category, since simplicity sets is monodal category, it's enriched over itself. The whole thing here actually lives in sim-set enriched category theory. So we actually have a sim-set enriched, the full sim-set enriched category of the category of simple pre-sheaves. And what these nice objects are is determined by these extra bells and whistles. And then by these extra excerpts, it follows that this thing is actually enriched in Kahn complexes, which is one way to think of infinity groupoids. So the whole thing will actually be an infinity groupoid enriched category, which in precise sense is a model of this category of infinity pre-sheaves, or what's called the global model structure. Let me put here globe. This is one of the central theorems of Urs big book on pursuing stacks on high topos theory. Okay, so this is something we can easily handle. This is just an ordinary functor category, and we take some subcategory. That's the simplest thing in the world. So I want to find a subcategory here that is embedded reflectively, that has left exact reflector that mimics the sheaf condition. Also here we are kind of lost maybe in the above line what this would mean, but for 30 years it has been known what one can do. It takes the same one categorical model here, the simplicity enriched category of simplicity pre-sheaves, but now puts on a different model structure called the local model structure. Takes again the subcategory of nice objects. Another central theorem of Urs' book. This is a model of the category of infinity sheaves or infinity stacks on X. And these two things are related. The two identity functors going here, which in terms of these models, of these presentations, called left bounds field localization. So the point is here is a nice abstract picture in high category theory, and we can handle it using generators and relations kind of presentation using one categorical data alone. This I'm going to do and call the resulting thing here, which you're starting to think of as being this complex and rich category here, nice objects and pre-sheaves, is my ambient context of nice Lie infinity groupoids.
Sorry. I'm just trying to master these higher categories. And there's this book by Leinster, who you surely know, and it is quite complicated, based on monad multi-categories. Why is that you have such a simple model, and the actual definition is quite involved and not even standard?
Yeah, I mean, as I say, so this model down here was proposed over 35 years ago. Originally a student of Dan Quillen proposed to model infinity stacks this way. And then I think for 30 years people, particularly those working on it, like Joyal and Jardine, they kind of guessed that what comes out of this prescription here is a nice model of something that deserves to be called infinity stacks on more abstract grounds. But it used to be undecided for quite a while, until 2 years ago when Jacob Lurie looked at things and figured out that there's an entirely intrinsic category theoretic way of talking about infinity toposes, who gives an entirely category theoretic description of these infinity stack, infinity toposes as these geometric embeddings into the pre-sheaf toposes, and proves that what people did for 35 years is in a very precise sense indeed a model for precisely this intrinsically correct structure.
So an infinity category or topos is easier to describe than an n category, n from n. Is this true?
That's actually right. You can look at truncations of these things here, the n-truncated objects. This involves more work than presenting the full thing. Yes, that's true. It has to do with the fact that these things are enriched in infinity groupoids So in a sense you can think of what's happening is that we take category theory and relax all equations that we might ever have imposed on the morphisms, relax them up to unbounded higher coherent homotopes. And we never impose by hand any restriction. That makes things actually easier to handle. When you want to do categories, you have to make sure that at the point where you truncate, things actually fit on the nose suddenly, which is not the case here. Yeah, that's kind of what underlies the thread, why this works so nicely, yes. Okay, so this is the answer I'm proposing. I won't be able to fully give you all the evidence showing that this is the right answer, certainly a plausible answer, and I'm claiming it's a good one. So let's look at, maybe as a first consistency check, let's see how we can continue and define these path infinity group faults in there. So this would be now ring point 2. We have now a notion of, oh yeah, maybe before I do this. No, actually let me postpone. Let me first do the pi. So the implicit statement, I already mentioned this. These things, string and fragment that I want, are in there. But actually to see this, I will use my pi to actually demonstrate to you that they're in there. So let me first introduce that. So again, an old idea. So Re2, that was the homotopy, the geometric smooth homotopy infinity groupoid on my smooth spaces. So here's another old idea. Old observation even, maybe. Or old, so first it's an observation, then it's made a definition. An ordinary topos, well, just a topos, yeah, I just emphasize now I'm talking about ordinary one categories for a second again. T is called locally connected. If the canonical terminal topos morphism, terminal geometric morphism, meaning a canonically defined functor that takes the topos to the topos of sets by, if it's a sheaf topos, taking of each sheaf the set of global sections. This comes with the left exact left adjoint, the constant sheaf functor, which is I'll call L const, because evaluated on some set is the sheaf of locally constant functions with values in that set. So if that always exists on general nonsense grants, it's this is the terminal Rosendick topos. It's called locally connected. The canonical terminal geometric morphism is what's called essential. It's an essential geometric morphism. Which means that this guy, which is left adjoint to gamma, has itself another left adjoint. I'm going to call capital pi mod pi 0. The motivating example is if T is sheaves on a topological space X, which notice is not the case I'm interested in. I'm actually talking about Grot toposes that are not defined as sheaves on a given topological space. But let's look at this motivating example, topological space, which is the usual shorthand, right, for sheaves on the category of open subsets of X with the open topology. Example, this is locally connected. Connected precisely if X is. That's where the name comes from. Right? So we think of the sheaf topos as giving us some generalized inclination of the space X, and we start characterizing the properties of X in terms of the properties of T. And you see this pi naught here, what it will do, it will take a sheaf, thought of as the corresponding étale space, as some space sort of modeled on open subsets in X, and sends a sheaf to its set of connected components. So to pi naught, of, let's give the sheaf a name of A. That's why I call this capital K to the 0th in a group. Okay, now you can already, or you should already guess what I'm going to say next. Okay, now look at what happens in this story is we start increasing the categorical dimension. Okay, now first replace Z by the two category of groupoids and T by the category of ordinary stacks, one stacks on X. This was done by Vaskis and maybe I mispronounced the other name, Poluzellos. Sorry, Vaskis et al. And they show, this thing exists precisely if the thing is locally simply connected. And this functor, the left adjoint functor, will be a pi1 functor that sends sheaf a stack to its first fundamental groupoid that recognizes the first fundamental group. From this you can easily guess how this continues, and this continuation is going to be my next definition actually. So we want something that detects these geometric multiple groups of our objects for all n. So I'll do a definition now, and then a theorem saying that what we've been talking about does satisfy this definition. So an ft1 topos of the kind I've been talking about, some left exact localization of some infinity free sheaf topos, is called by me now locally contractible, right, locally infinity connected, if the canonical terminal infinity geometric morphism that takes Gage to infinity topos of infinity groupoids, which you maybe should think of as being infinity stacks on point, then you know precisely what it is. Well, as far as I've described it, bottom line here. This will still be called gamma, right? It sends a smooth infinity groupoid here, a Lie infinity groupoid, to the underlying infinity groupoid where we just forget the smooth structure in the kinds of examples that we want to be thinking about. So this does have a infinity left adjoint, which I still call L const. It sends an infinity groupoid to the constant infinity stack of locally constant infinity stacks with values in that infinity groupoid, whatever that means. And we say the thing is locally contractible if this further left adjoint exists, which I'm just going to call pi. It's not yet my boldface pi, that will appear in a second, this is just ordinary pi. Maybe you could write pi infinity, but since this is sort of fundamental thing, I'll just call it pi. If the canonical inform is essential, which just means that this thing exists. Let me first again give the historical example maybe, and then my proposition. So this is example sort of theorem. Let's play the same game with the topological space to get some feeling what's going on. If H is infinity sheaves on X, again our topological space. Topological space. Which is a locally contractible base, which is locally contractible. Then pi exists. And if we may think of the topological space itself as sitting inside H as the terminal infinity stack, the étal space that's just X itself sitting over X. And if X in H denotes the space, well, let's assume it's on the space X itself. Sorry. Itself as an object in H, then we can ask, okay, what's pi of X, terminal object? Some infinity groupoid. Let's take, well, first I mean, this is the fundamental infinity groupoid of the topological space. What does this mean? If we take the ordinary geometric realization of that, there's geometric realization of simplified sets to topological spaces, and we have something in top, then this is weakly homotopy equivalent to X itself. So this thing takes indeed an object in the category of sort of higher spaces modeled on X and produces a geometric higher homotopy groups. So this is the proof of this, maybe. Turns out this is an point result from 68. This is Martin Mazur, 1968, plus a little exercise in translating the model category language that I presented into the older language of. They implicitly use the category of finite objects there, so they did something that looks a bit different, but it's actually precisely this. So they did compute this pi of x back then and proved this theorem. There's a nice review in this little booklet by Ike Murdyk on cohomology and homotopy of toposes, where there's a very nice review of this. Okay, so maybe continue here. So we're interested in our broad toposes. You all want to know now what is the case for the smooth, for the Lie infinity groupoids that I keep talking about. So if I take here infinity sheaves on this abstract category of just Cartesian spaces. So proposition this thing is locally contractible. As are in fact all infinity stack toposes which satisfy the property that on the representable objects here of the site we use to present them, the constant infinity pre-stacks satisfy the set. This one, how one proves this, I'm not going to say this. So what this does have, this property, so claiming now in the smooth context that we're in, we do have this functor pi. Thanks. I'm about to state the last statement. It's 5 minutes to go, or is it 5 minutes over?
To go.
Yeah, I'll state my main statement now, then just indicate how the story proceeds from there. So we do have a way now to take such a very generalized, smooth object and turn it into an ordinary infinity groupoid, and then by geometric realization into ordinary topological space. So in my category of Lie infinity groupoids, the canonical normalized, ignore this for a moment, Lie algebra 3-core cycle, mu 3 in the Einberg algebra of the Lie algebra of SOT. This is a Lie algebra. It has a canonical 3-core cycle, which just comes from taking the killing form, combining with the Lie bracket. It can be normalized such that it represents the generator in the Ram cohomology on spin D cohomology, and that's the normalization we need. So there's some Lie algebraic data here. Integrates in H. So this will not tell you much now. I'm just saying because it's kind of important in order to actually identify that we do have the right smooth thing here. It does connect to the Lie algebraic data that you would expect. Integrates in H to a 3-core cycle of smooth Lie groups, namely a morphism. Oh, sorry, I need more space. So that's the smooth Lie group spin that we've already seen in the toy example, and that's its delooping to a smooth classifying space in my smooth topos. So as a smooth infinity groupoid, this is just the group regarded as one object, smooth groupoid. But we have now in H a morphism, which I'll call int mu3 of the universe Lie algebra 3 cocycle, to the Lie3 group point that I obtained by taking the Lie algebra U1, the circle, the smooth circle, and suspending it, delooping it 3 times. So I'll form the smooth Lie strict actually 3 group point that is a single object, a single 1 morphism, a single 2 morphism, and then U1 is a circle worth of 3 morphisms. So this morphism, as the first statement, exists. It sort of integrates this Lie algebra 3 cocycle. We can look at its homotopy fiber, this inclusion of the point here, going to the unique point. And we can take the infinity pullback in H of this. And this is an object which I'll identify with the string D. What outcomes here? A Lie 2 group point, something equivalent to a strict Lie 2 group point, which is string D, and which you can actually write as a strict Fréchet Lie 2 group point whose space of morphisms is the path group of spin D. Sorry, the space of let me do this differently. So if we do string D as a smooth 2 group, it will be the 2 group, or the space of objects is the path, smooth path group D, whose morphisms is paths in D times loops in spin D, spin D, where we take this group, the standard Kac-Moody central extension of weight 1. Whatever this means, there's a nice smooth incarnation now in our generalized context of the smooth space of the string thing, and similarly for the Lie algebra 7 cocycle and 5 brane. So we can play this game again. Form a multiplication of a 6 cocycle on string D and get the smooth realization of 5 brane, such that, and this is now the punchline, if we, if we apply our pi to it, we do recover. So I can take the smooth object, string D here, turn it into an ordinary infinity group point. This will be the topological string group, because finite topological space is the universal 3 connected cover. That was the thing that we tried to refine to something smooth in order to say what its differential commodity is, and so on. 5 brane sits here. And gives indeed the underlying is the ordinary topological 5 brane. So we find this Whitehead tower of ON here smoothly realized in this sense in H. And then if you remember the second item I stated on the board, we can now define using this pi. Can define what it means to have string D and 5 brane D, principle 1 with smooth parallel transport that we can use to describe the physics. Thanks.
Other questions? Jamie.
What relevance does the internal logic of the infinity topos have to this picture you've been describing?
Yeah, so I thought I was going to ask this question here to the topos theory guys here. So I'm not thinking about these topos. So there's these two ways of looking at topos, right? There's geometry, there's logic. So I'm just using the geometry. You may have seen we had the discussion with Mike Schulman, right, on the blog. So it seems that the well, no, I'm not going to say anything more about this. I don't know what a good statement about logic here is. This is topos in the sense of generalized geometry. But I'd be interested to learn what the internal logic is. What's the internal logic of the sheaf topos on manifolds? The one where differential spaces, mapping space live in. What's the internal logic of this? If you have a good answer to this, maybe it's kind of obvious what the one here will be. I sort of suspect it won't be anything very interesting because it's not the right perspective on this thing. This is not a logical thing, but who knows? I mean, I think it is.
Any other questions?
If I remember well, you have a paper connecting topological quantum field theory to algebraic quantum field theory.
Yes.
Does that fit into this?
Yes.
Somewhere?
So this is the step 3 that I indicated. So we have here these pi things. So if I have a morphism from some pi x to somewhere, return to my h, what will it be? It will take paths gamma prime in x and send them over to fibers here of certain bundles sitting over the endpoint, certain morphisms between these fibers according to parallel transport, the phases assigned to these trajectories. So that's an x. Now we're talking about, well, you can regard these morphisms as encoding differential cocycles in H. So for differential cocycles, there's a notion of push forward. So somehow you can imagine that if we have such an x and your sigma maybe, and we had our differential cocycle nabla on x, we can put it back to a differential cocycle on this product thing here. And then we have the projection here to pi on sigma. Right? There's general formula for push forward of commodity theories as soon as the A here is sufficiently nice. Doesn't have to be just a stack-loaded bifurcation so that we can push. Then you imagine that you can perform a push forward here and get something, some differential cocycle down on x. And I indicated what that is in the case of parallel of quantum mechanics. It's just a time propagator. And in that article I show that if on sigma, if you take sigma to be two-dimensional, and you do have a parallel transport on this, which assigns something to paths in sigma, then you can form its endomorphism coprieff by assigning to each open subset, regardless the interior of such a path, the endomorphisms, two endomorphism of the image of this morphism in a target, then the resulting coprieff is the local net monoids. So there's some gaps to be filled in how precisely the push forward works, but what I show in this article is that if it works, then the outcome is of the right form that you would expect a quantum field theory on sigma to be like. So in particular, the conformal field theory on the string, on sigma here, plausibly can arise this way, but we're still working on actually doing the push forward. We started approaching this from both ends. Okay, thank you.
Okay, I would ask Judy for further questions, the coffee break, so let's thank our speaker again.